So, once again, we're kind of rehashing in a more general situation, something that we knew about before, namely bases, right? And the notion of linear independence. So let's kind of recall. So let's suppose that D is a vector space. A set of vectors in D. So these vectors here, B1 up to BK, they are all vectors that live in D. So this is actually the exact same definition that we had when we were in RN. Anybody know what it means to be linearly independent? What does it mean for this set vector? Yes.
The determinant is non-zero.
Well, I want to do this in a more, so you're talking in terms of matrices, right? And unfortunately, so suppose that these are row vectors that are very, suppose these are column vectors that are very big, right? Suppose here's what the problem is. You suppose those two vectors are linearly independent? What's the clue here? So, do you remember what? Do you remember how we told these kind of vectors when we put it in the matrix? So if you put it in the matrix here, these two vectors, these two column vectors, linearly independent. Oh, some controversy here. What's the rule? How can we tell? We need there to be, we need every column to be a pivot column. Is that the case here? Yes. These are linearly independent. So let's get back to brass tacks. What's the basic definition? When you have a linear combination of the two vectors equaling the zero vector, what must you be able to say about these two? It forces them to be linear. It forces these two constants to be zero, right? And look at what we get when we put this together. We get C1, C2, 0, 0, 0. Right? This forces C1 to be 0, C2 to be 0. So they have to be linearly independent. Everybody okay with that? When we put it in the matrix, what that means is that every column is a pivot column. Now, yes, there are special things like if it's a square matrix, we look at the determinant 0 or whatever. But the problem is you can't do a determinant for this at all, right? Because this is 5-row column matrix. So what does it mean to be linearly independent? Like, for example, if I ask you what's the definition on the next test, which I could almost guarantee something fundamental like this might be in there. So here we go, money in the bank. If this condition forces all the constants to zero, that's what it means for a vector to be linear. Yes.
If we just write like the solution to the homogeneous equation, like matrix M with columns like vector.
That's not general enough for the general definition, and I will give you an example. I am glad you asked that question. You remember how we talked about this as a vector space? These are all polynomials of degree 2 and smaller, right? So this is the set of all polynomials that look like this. What happens if you add two polynomials that are degree 2 and smaller? What do you get? A new polynomial of degree 2 and smaller, or smaller, correct? What happens if you multiply a polynomial of degree 2 and smaller by a scalar, by a number? Still degree 2 or smaller, agreed? This is a vector space. Now, this set of polynomials, 1x and x squared is linear in the set. And so now you see the limitations of matrices, right? Because these are just, this is just a variable x, right? I mean, what are you gonna do with the matrix here? Actually, this can correspond to a matrix, but we'll talk about that later. So suppose that a plus bx plus cx squared equals 0. We need to show that a, b, and c are all 0. Now let me point out that this is for all x. Well, so what does it mean? Here's a fancy way to write 0. It's 0 plus 0 x 0 x squared. How do you equate two polynomials? By the coefficients, right? So this is a linearly independent set. Okay. Let me give you another example, and you can do the next example the way I did this. I just did this kind of polynomial comparing coefficients, right? Which is actually, this is probably the way that you did Taylor series, right? When you were in Calc 2. Let me show you kind of where this comes from and why for all x's. You're not solving for a particular x. You're not solving your quadratic equation here. This has to be true for every x. Let B be the set of, let's say, from okay, so this is like a Calc 1 thing. What is this collection? These are all continuous functions whose domain is the interval from 0 to 2 pi. Right? Output is just a middle number. There's all kinds of crazy crap here. Any polynomial you can think of, inverse, yes, inverse tangent of x forward, 1 over 1 plus x squared, the trig functions that are not, that don't have a singularity in between their sine and cosine x. Let me give you an example here. Actually, let me go a little bit further here. Show 1 sine x cosine x as a linearly independent. And actually, this is very, how many of you have ever heard of Fourier analysis? if you're an engineer, then you might encounter this at some point later, especially if you're an electrical engineer. for example. And the fact that these are linearly independent is very important. Okay, so how are we going to do this? Well, suppose suppose that you have this linear independence relation, or this linear dependent relation. What you need to do is you need to show that A and B and C are all zero, right? And like I said, we did this problem, the previous problem, whether we did this too. Any ideas? How are we going to show this? This is rather confusing. We're trying to show some kind of results here. We're trying to show that these three functions, one, sine x and cosine x, are linearly independent. Right? And I'm going to plug in and use some linear algebra. So here's my master equation. And after I do this first step, maybe you'll see how it follows through. This has to be true for every x between 0 and 2pi, right? So in particular, it's true when x equals 0, right? So let's plug in x equals 0. And what do we get? What's sine of 0? 0. And cosine of 0 is 1. So I get A plus 0 plus C is equal to 0. Agree? Plug in pi over 2. And that gives me A. What's the sine of pi over 2? 1. So let's say it's big. And what's the cosine of pi over 2? 0. What else might I plug? I mean, you can plug in, square root of pi over 37, but we're not to make things difficult. Plug in pi for x. A. What's the sine of pi? 0. What's the cosine of pi? -1. So we have these three equations. Everybody okay with that? Add these two equations here. So see, we're doing linear algebra to do linear algebra. What happens when I add these two? I get 2a equals 0. So immediately I get a equals 0. But if a equals 0, then c equals 0. And now a is 0, so b is 0. So these three functions are linearly independent. Yes,
Would it still be linearly independent if you had a tangent in there, since a tangent's a sine and a cosine?
tangent's not continuous on the center,
Oh,
right? The tangent pi over 2 doesn't exist. Let me ask you this. Same example. What about that? Is that a linearly independent set? this is a linearly independent set. What about one in sine squared and cosine squared? That linearly independent?
Well, I don't know, the sine squared plus cosine squared can simplify to one, right?
Uh,
So I bet you it's something to do with that.
what does that come to? This comes to, this is a 1. That's a -1. That's 0 for every value of x. Agreed? So there's a linear combination of these. Are all these coefficients 0? No, right? So this is linearly dependent. Because you can write a linear combination of it being 0 without all the terms being 0, without all the multipliers. Any questions on that?
Why is it negative?
I'm just emphasizing, it's -1 times this, plus 1 times this, plus, see, that's playing the role of A, B, and C. Yes,
So with the previous example, of like sine cosine, how, we're gonna like sine of like pi or 3/4 pi cosine. Just pretty much like √2 and -√2. Like,
so you're saying take this to be 0,
and then B and
X
C
equal-
have to be the same.
but see, this, for this to be, this has to be 0 for every x,
Oh,
right? This has to hold for every value of x between 0 and, not just 1. Yes.
If I like forget that sine squared plus cosine squared is 1, is there a point where I'd be solving and realize that it's linearly dependent, or is that the only way to know this?
Yeah, it's a good question. I'm not really sure how to answer that. I think it, because this is a linearly dependent set, and there are many, actually, there's infinitely many relations, but I think they'll probably almost all hinge on sine squared x plus cosine squared. Other questions? Okay, so, let me remind you also, so we've got a new analog here of basis. Oh, actually. If B1, B2, BK is a linearly dependent set, then one of these in here, one of these vectors and in fact, the converse of this theorem is true too. That is to say, if one of the vectors is a linear combination of the others, then it's linear set. This is why this is true. Suppose that these vectors are linearly dependent, then I can find an equation that looks like that, where not all the C's are 0, right? At least some of the C's are not 0. Everybody okay with that? So all of these C's don't have to all be 0, so there is some this is not equal to zero. That's what it means to be linearly dependent, is some of those C's are not zero. Yes,
Don't all the C's have to be the same thing? I would be like, well, you can multiply like individual elements by anything you want, and if they eventually come out to be zero.
yeah, but for example, if C2 is twice as big as C1, no matter what you multiply by, this will be twice as big as C1 in absolute value. Right? If this is a 2 and this is a 4, then if you multiply it by 7, now you go to 14 and 28, and so forth. So suppose this is not zero, this means that Ci dvi minus C1 d1 minus C2 d2 minus Ci minus 1 di minus 1 minus Ci plus 1 di plus 1 minus Ck d2. And all I did is I took all the stuff that wasn't CIDI to the other side, and that's why they've all got minuses. And now divide by C1. Or I'm sorry, CI. And what do we have? We have BI is a linear combination of the others. And the key part of this is just the fact that CI is not zero, so I can divide by it. That's all there is. Right? Any questions? Okay. This is actually useful to know that these are kind of equivalent notions. Linearly dependent set, one of the elements can be written as a linear combination of the others. I should say maybe at least one of the elements can be written as a linear combination of the others. Let's let okay, let's suppose we have a vector space V, and let's suppose that H is a subspace. Can somebody remind me what it means to be a subspace? What three things do we know about H? Yeah,
Has to contain the zero vector.
H contains zero. What else?
Closed under scalar multiplication and addition.
That is correct. So if you got two vectors in H, add them up, they're still in H. If you got a vector in H multiplied by constant, it's still in H, and it's got the zero vector. Right. A set, let's say. A set fancy B, which is maybe vector B. I'm sorry, vector A is the basis. Yeah. Anybody remember what we needed for basis?
Nearly in this expansion.
What was that?
Linearly in the expansion.
You gotta have two things going on, for this set to be a basis of the thing. Number one, B spans. What this means is every single vector in H can be expressed as a linear combination of those K vectors there. Everything in there is in the span of this. And two, you need this to be linearly independent. So it's a spanning set, and Simon, I think you said last time, something economical, like the smallest spanning set, and we're gonna see a theorem in a moment, that's exactly true. Right, it's a spanning set, so it spans everything in H, and it's the smallest possible, that automatically forces linearly, independent. Let's look at a couple of examples here. Uh, um, for Rn. And this is actually called the standard basis. Because everything in Rn, let's suppose you have a vector A1, A2, A3, all the way down to An, is A1 times this, A2 times this, A3 times this, da, 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 all the way up to An times that. And it's easy to check if this is actually a linear independent set as well. Here's an example. Anybody want to guess what a basis P2X is? Let me quickly remind you, this is a set of all polynomials of degree 2 or smaller. I want to guess a basis for this one.
Columns of the.
You're being too sophisticated. We're going to get to how this ties in matrices. But I mean, in terms of elements in there, in terms of polynomials, can you give me 3 polynomials that make a basis?
CX squared dx.
What's that?
Would it just be CX squared dx? Like, all separate.
Well, let me strip that down. We already know, you've shown earlier in class, this is. Actually, we've shown the hard part, that's linearly independent. Can somebody explain why it spans? Why does this span all the 3 polynomials?
Is all polynomials like have of that degree of 3 elements, just like set maybe and C.
Typical garden variety degree 2 polynomial looks like this. See, that's what they all look like, right? How can I write this in terms of the basis? Well, this is just A times 1 plus B times X plus C times X squared. Everybody okay with it? So now we see that that set spans, B spans degree. Any degree polynomial can be written as a linear combination of that. Okay, so let me ask you to make a wild, crazy conjecture. What if we had P5x? What if we had all polynomials of degree less than or equal to 5? Anybody want to guess a basis?
1x squared x cubed x to the fourth.
Yes, that will work. 1x, x squared, x cubed, x4, x5, right? Okay, how about another? Here's one that's a little bit kind of out of what we talked about. What about all polynomials? That's a vector space, right? Except I don't have any requirements on the degree all being less than 2 or 5 or anything like that. You can have any polynomial. Anybody want to guess what a basis should be for that?
The series from n is equal to 0 to n of x to the n.
Well, that's a series, right? That's power series. So take the separate elements out. 1, x, x squared, x cubed, x4. Don't make it clear. Actually, that's the first example of something that we've seen that actually has an infinite basis. So we don't really talk about that much here, but it is an infinitely large, linearly independent set. And every polynomial is a linear combination of some finite number of elements. Let me also leave this example with the following. Give me a number. 8. Brian, give me 2 numbers. Give me 3 numbers.
3, 7.
3, 7. This is also a basis. Can anybody make an argument? This was, I'll let you kind of think about this. This is really a little bit more obnoxious. And actually, the linear independence is a little bit easier this time. Yes.
Because there's always gonna be like some element of the next higher thing that's unreachable by the previous one, no matter what one.
Oh, that's a very good intuitive argument. Yeah, I agree with that. So this is a linearly independent set, because if you multiply A times this, B times this, C times this, the C has to kill the x squared term, because these can't inflate up to x squared, so C has to be 0. So that's gone. So now you have A plus A times A plus B times this equals 0. Well, the B has to be 0 because it's got to kill the x term, because you can't get it from there. So now that's 0. So now you got 8A equals 0, which forces A to be 0. Now, can you prove that every polynomial in P2 is a linear combination of those? And the answer is yes. And this actually sort of goes back, the computation you would use is almost like a matrix. We just set up an arbitrary polynomial like this and start solving, and you will get a matrix to reduce. So see if you can power your way through that. Any questions? Okay. Here is a theorem, and I alluded to this a little bit earlier. This is called the spanning set. Okay. So suppose I collect a set of vectors. I just got these k vectors, v1 up to vk. and let H be the span of B one up to B K. Right, so it's just, I look at all these things that spans. A. If one of these vectors, BI, is a linear combination of the others. Okay, so if one of the vectors in here is a linear combination of the others, by the way, somebody paraphrase me. What am I saying about that set B one up to BK? I am saying that that set is linearly dependent because one of those things in there is a linear combination of the others. Agreed? Then H is spanned by set S minus BI. So what I mean by this is the set S with BI removed. So if one of the vectors, say BI, is a linear combination of the others, you can just jerk it out. Just take it out of there, and you're still spanned by the set here. Well, with BI removed. And two, if H is not equal to just the zero vector itself, then some subset of F is a basis. Okay. So let me try to explain this to you a little bit. This first one is kind of a very important statement. It says if one of the vectors can be written as a linear combination of the others, you don't need to use that vector in the spanning set. Right? So why is H? Once we figure out why A is true, we're going to use it to figure out why B is true. Suppose okay, so I claim that H, which is the span of D1, DI, DK, is equal to span of D1, DI minus 1, DI plus 1, DK. Yes.
Does VI actually exist, or is it just a representation of all the linear dependent combinations you can make?
No, it actually exists. It's one of the vectors. There may be many of these vectors that are linear combinations of others. I just picked one of them. Right? It just turns out that, so for example, running a parallel concrete band in R3, suppose I have vectors 1, 1, 3 minus 1, 1, and vector 5 minus 2, 1. Right, in our three, so let A do this. Now notice, see by C, one of the vectors is a linear combination, the other is what?
Oh, yeah, the middle vector is a combination of 2 to the far right vector, so 2 times.
Right.
The one on the far right, and then
So this, in our case, would be my BI. Because my 521 is actually equal to minus 2. Or let's see, that was 1. Minus 1 times vector 101 plus 2 times vector 3 minus 2. And that's exactly what we have written here. We have BI as a linear combination of the other vectors. Everybody okay with that? So I claim, so the analog here is if H is the span of this should be the span of 101 and 3 minus 1. Can somebody explain why the spans are the same? That's essentially it, really. So here's why this is true. Suppose you have everybody agree that this is what a typical element of the span of these three vectors looks like, right? Well, here's the deal. I can now write this middle vector, in this case, as, let's see, we know this one is this, minus 101 plus 2 times 3 minus 1, 1. That's just replacing that middle vector, 5 minus 2, 1, with this. Correct? And now I can farm this out to the other vector, right? So this is the same thing as if I expand this out, what should my multiplier of vector 101 be? Correct. And it's now a minus b. And what should my multiplier of vector 3 minus 1 be?
C plus 2.
Right, it should be 2b. Right. So what we've shown is anything that is spanned by this can be spanned more economically by just these two vectors here. And the proof for this is almost exactly the same, because what you do, this is playing the role here of the minus 101 and the 2 this. So let's say D1 D1 plus D2 D2 plus VI VI DK DK. Now, what you can do is replace the VI by this. Which is awful, but you can do it. And now multiply this through and group this with V1 all the way up to VI minus 1. And now you've got this linear combination with one less factor.
That works for as many vectors as you want, right? Say if you have a set of n vectors, if two are linearly dependent, if you remove those two, then that will still work, right?
Well, you have to do it inductively because the problem is they might cross over in the representations they use, right? So if you do two at a time, you're dangerous because if you remove VI and VJ, and VI has a VJ component in it, and VJ has a VI component in it, when you put it back together, you get the VIs and the VJs back. So if you do it one step at a time, you can eliminate it. Yes.
That's supposed to, I hope it's not AI times. Vector,
Where are we at?
on the top one,
Right here?
or for the, on the left, and it says vector VI,
Yes.
why is there not an A?
Because what the statement said in the original one is one of the vectors is a linear combination of the other. And one of the vectors here is just VI. I mean, it doesn't matter if you put an AI there, you can just divide out by it later, right? As long as it's not zero. Okay, other questions? Okay, so what part B says, or used to say. So let me remark on B. So what is the upshot of this? So if you have H. If no VI is a linear combination of the others. Then V1 up to VK is a basis. Everybody okay with that? Because if no VI is a linear combination of the others, that means this is a linearly independent set. And they span H by definition. I've just declared that H is a span of that. So there you go. If one VI is others, then remove it. And now you have H is equal to the span V1, VI minus 1, VI plus 1, VK. And you have one less vector. Now repeat the process. Right? Now look at this set here. If none of these are a linear combination of the others, then you've got your basis. If one of them is a linear combination, remove it and get one less. This process must terminate unless H is the zero, unless H is a zero vector subspace in the first place, and in which case this would have been the empty set anyway. So it's just technical reasons why we have to write that last part. But this comes full circle with this business about being economical, right? Start with your spanning set. If it's linearly independent, you're done. If not, one of the elements is linear combination, the others, throw it out. Now you get a slightly smaller set. If it's linearly independent, you're done. If not, throw another element out, and you eventually get to a point where the set must be linearly independent. Okay, any questions on that? Good questions, quit. Are there any questions? I guess, I will have your quiz posted later this afternoon, probably. Otherwise, you guys have a good one. We'll see you on Friday.
So, in my 10, 20 minutes, I forgot to give you